Hello, this is the second part of third lecture of linear algebra, and this part is about invertible matrices and determinants. Let us consider a square n times n matrix A, and let me remind you that the matrix A is said to be invertible if we can find another square matrix B, also n times n, such that AB equals identity and BA also equals identity matrix. Okay, this theorem summarizes all possible equivalent ways to say that matrix A is invertible. These all equivalent conditions, and the first condition is basically by definition that the matrix A is invertible, and the remaining 10 conditions give you alternative ways to check that matrix A is invertible. So, for example, condition 2, it's a simplified version of condition 1. It basically only tells you that A times B equals identity, but this actually implies that B times A also equals identity. In the case when n is 2, this is tutorial program. Okay, we don't have time to go over all of these conditions. The proofs are contained in the lecture notes, so I strongly encourage you to read the proofs, or maybe it's better to try to prove the theorem by yourself. But let me just check that condition 1 and condition 2 of the theorem are equivalent. So let me prove that condition 2 basically implies condition 1. Okay, to do this, we fix two square matrices, A and B, both n times n, and we suppose that AB equals identity matrix. We have to check that BA is also equals identity matrix. Okay, how to do this? So first of all, we let C to be matrix B times A. We want to prove that C is identity. Let's assume it is not. We suppose that C is not an identity matrix, and let us use this to derive a contradiction. If we can derive a contradiction from this assumption, this is basically going to prove that C is identity matrix. This is exactly what we want. So first we play a little bit with the matrix C. We multiply it by matrix A. We simplified it like ABA is the same as AB times A, but AB is identity. So this is nothing but identity times A, which is A. So we get AC equals A. Now, of course, we can rewrite it as A times C minus identity equals 0. Here, 0 is a 0 matrix. Okay, what does it mean? It means that A times some non-zero matrix equals 0. And keep in mind that C, by assumption, is different from identity matrix. So C minus identity is not a 0 matrix. In particular, at least one, its column is not a 0 vector. But when you multiply matrix A by this matrix C minus identity, it's roughly the same as multiplying A by each columns of the matrix C minus identity. So at least one such product is not 0. So basically, if we take column, non-zero column of this matrix C minus identity, if you multiply it by A on the left, you get a 0 vector. What does it mean? It means that this column is contained in the kernel of the matrix A. So in particular, kernel of the matrix A is not 0. It contains a non-zero vector. So in particular, nullity of the matrix A is positive. Dimension of the kernel is strictly positive. It's not 0. Okay, this is something. Of course, we're going to use rank nullity theorem at some point. First, let me remind you what is a rank of a matrix. Rank of a matrix is dimension of its column space, or equivalently, it's dimension of its row space. Let's consider column space of A. Column space of matrix A consists of all possible vectors in m-dimensional space. Here, of course, it's a typo m is supposed to be n, such that this vector y is represented as A times x. This is a very important observation remark, which we used already several times. And let me repeat it. So column space is a span of columns of matrix A, but it's the same thing as all possible vectors A times X, where X runs through all possible vectors in Rn. So again, this product AX is a linear combination of columns of the matrix A with coefficients x1, x2 up to xn, where xi is entry of the vector x. Okay, so this is as a column space. Okay, but look, we have this condition AB equals identity. So if instead of x here, you substitute the first column of vector of matrix B, what do you get? You get A times this column is first column of identity matrix. But the first column of identity matrix is vector 1, 0, 0, 0, 0, which we usually called E1, standard vector, first vector in the standard basis of Rn, of n-dimensional space. Similarly, if you take second column of matrix B, if you multiply it by A, you get a second column of the identity matrix, which is a second vector in the standard basis of Rn. And continuing this process, we see that column space contains E1, E2 up to En, where these are standard bases of the n-dimensional space. Okay, but what does it mean? It means that column space of A contains the span of these vectors, but span of these vectors is the whole Rn, of course, because it's a basis of Rn. So we just proved that column space of A is the whole n-dimensional space. Okay, but this means that the rank of A is n, because the dimension of Rn is n. But it contradicts rank nullity theorem. If rank of A is n, then rank nullity theorem tells you that the dimension of the kernel is 0. The nullity of the matrix is 0. But we already proved that kernel is not 0. This is a contradiction. Okay, this contradiction implies that AB equals identity, implies BA equals identity, which is very handy. It means that in the definition of invertible matrices, you only have to check one equality instead of two. Okay, starting from now on, we consider a new topic which is related to the topic of invertible matrices, but we will go back to this a little bit later. So the new topic is determinants. Okay, we already mentioned determinants several times, implicitly and explicitly in tutorial problems in the previous lectures, and probably many of you already met determinants in high school. Let me start with determinants of 2 by 2 and 3 by 3 matrices. If you have 2 by 2 matrix A, which you can list like this, A, B, C, D, then by definition, its determinant is the number AD minus BC. You just multiply AD minus BC. Yeah. So this probably familiar to you. If not, it's absolutely okay. We basically consider this topic from the very beginning. So my advice, when you see the matrix ABCD, 2 by 2 matrix ABCD like this, my advice immediately, if you can, immediately compute its determinant. So this AD minus BC, these numbers should be basically subconsciously computed every time you look at 2 by 2 matrix. Okay, so another just a minor, a small remark that quite often determinant is denoted like this. If you have A, B, C, D, and instead of usual brackets, you put these brackets vertical double columns, then in many books, this is a shortcut for determinant. We're going to use this shortcut from time to time. Okay, if now you consider 3 by 3 matrix, then you can define determinant using this formula, and this formula also gives you a nice pattern. Namely, look what this formula is. We take the first row of this matrix. You see A11, A12, A13 is the first row, and then we write down the following interesting looking sum. we take A11, and then we multiply A11 by the determinant of the matrix obtained from A if you remove first column and the first row. Yeah, you get this matrix and we put this determinant. Similarly, the second term in the sum, it's A12 times determinant of the matrix obtained from A by removing the second column and the first row, and then multiply by -1. And then the third term of the sum, you take the final entry of the first row and A13, and you multiply it by the determinant of the matrix obtained from A by removing the final last row, last column, and the first row. Okay, and with a sign plus. Again, you see this, we change sign every time in this sum. This goes with plus, this is with minus, this is with plus. Okay, you can use this pattern to define determinants inductively for matrices n times n, square matrices n times n for any n. If you already know what is determinant of 2 by 2 matrix, you can define what's determinant of 3 by 3. Using the same pattern, if you already know what's determinant of 3 by 3 matrices, you can define determinants of 4 by 4 and so on. Okay, this is called inductive definition of determinants. So let me just basically summarize what I just said. To do this, let me denote the matrix obtained from A by removing ith row and j's column by this symbol Aij. Yeah, so this is going to be n-1 times n-1 square matrix obtained from A by removing ith row and j's column. And then we can define determinant of the matrix A using this inductive formula. You have this sum similar to the sum on the previous slide with changing signs, plus minus, yeah, and starting from 1 to n. So look, first you take A11, yeah, and then you multiply it by the determinant of the matrix obtained from A by removing the first column and the first row. Then with a negative sign, you add minus, basically subtract, yeah, A12 times determinant of the n-1 times n-1 matrix obtained from A by removing this column and still the first row, and continue. Using the sigma notation for the sum, this can be expressed like this. Yeah, you have this. This is usually called expansion formula for the determinant when you expand determinant by the first row. Yeah, okay. So you can use this formula as a definition of a determinant. So if you know how to compute determinants of n-1 times n-1 matrix, you can apply this formula to define what is determinant of n times n matrix. Okay, I must warn you that in different books, determinants can be defined in different equivalent ways. So this is not the unique way how we can define determinants, but this is very handy way. It's also give you a formula how to compute determinant, yeah, in every given case. Okay, so the next slide basically contains generalization of this formula when you can expand determinant by any rows or even by any columns. Let's take a look on them. So again, we fix n times n matrix and we have the following proposition. Now, this is not a definition. Now, this is a proposition which can be proved using definition of determinant given on the previous slide. Yeah. What is this? This is expansion of determinant by, in this case, ith row. You fix I. In the previous slide, I was 1. It was the first row. Now you can take any I. So, for example, it can be 2. Yeah. And then you consider the same sum as before, but you replace A1j by Aij everywhere. And here, minus 1 to the power of 1 plus j, you replace by minus 1 to the power of I plus j. Yeah. This is a very nice formula. So basically, why do you need this formula? Because it's sort of clear if you have one row with a lot of zeros, that the sum becomes simple. Yeah. So maybe the first row is not the correct row to start with applying this formula. Yeah, maybe you need to take another row, the row with a lot of zeros. And similarly, the same formula exists for columns. Yeah. So here, this is the same, almost the same formula as here. The only difference now that you take summation not by I but not by j, by I. So now j is fixed, and j now it's basically the number of a column. You take any column. For example, you can take the first column. In this case, this means j is 1, and you write down the same, absolutely the same formula as we did with a row, but with a column. You take a11, and you remove this row, you remove this column, and you multiply a11 by the determinant of the matrix obtained from A by removing this column in this row. Yeah, this n-1 times n-1 matrix. And then you subtract A21 times determinant of n-1 times n-1 matrix A obtained from A by removing second row and the first column, and so on. Yeah, this very handy formulas which you can apply easily when n is small, especially 2 and 3, and 4 as well. And the formula becomes quite simple when you have a lot of zeros as entries in your matrix. If your matrix consists of many zeros, then this formula becomes very simple. So for example, if you have a zero matrix, then of course everywhere here you have a zero. Yeah. Okay, let's consider some examples. So the simplest, probably the simplest matrix after the zero matrix is an identity matrix. Yeah, if you have identity matrix, then its determinant is 1. Again, this follows immediately from our definition, from the formula which we used. I strongly suggest to try to prove, not to try, but I strongly suggest to prove this by yourself. Just basically apply the formula on the previous slide. Okay, absolutely in the same way, you can generalize this formula for the identity matrix, and you can prove that if you have a matrix consisting of all zeros except diagonal, such that on diagonal you have some elements lambda 1, lambda 2, lambda n, then its determinant is just a product of diagonal elements. Such matrices are called diagonal matrices. Diagonal matrices are quite simple. They're easy to work with. Okay. If you play a little bit around with the same formula, you can get absolutely the same formula for the what is called upper triangular matrices. These are matrices such that below diagonal, like here, you have all zeros, and on top of diagonal, you have any numbers. Then the same formula applies. Basically, it follows from our definition. Yeah. Or you can consider what is called lower triangular matrices. So now it's below diagonal, you have arbitrary numbers, and on top of diagonal, you have zeros. You still can apply the same formula and you get zeros. Yeah, it's all more or less follows from our definition and proposition on the previous slide. Okay, this is an example how you can use expansion formulas from the proposition on the previous slide. In this case of 4x4 matrices. Matrix. If you look at this 4x4 matrix, you notice that the third column consists of almost entirely of zeros. Yeah, there's only one number 3 here. If we had 0 here, then clearly the determinant going to be 0, because we can expand this determinant by the third column. But now we still can expand this determinant by the third column, but the only one summand in this your expression survives. This is the summand -3 times determinant of this matrix obtained from this 4x4 by removing this column and second row. Yeah, you have this. Now you can apply again the same expansion formula, for example, for the third last row, and you get this. Yeah, and then you compute it 2x2 matrices. The formulas for determinants of them is not very complicated. Here is just AD minus BC, 1 for minus minus 1 times 2, yeah, and same here, 3 times 4 minus 4 times 2. You simplify, you get 150. This is absolutely classical. Okay, good. So now let us consider discussing some properties, deep, interesting, important properties of determinants, which actually follows from the definition and from the proposition on the previous slide. But they do not follow immediately. You actually have to prove these formulas. Actually, also you have to prove the proposition on the previous slide. The problem is this goes a little bit beyond the scope of this course. So I decided not to put the proofs of most of these results in the lecture notes. You can look for the proofs in the book. You can find the proofs in the internet, on Wikipedia, in a lot of linear algebra books. In the lecture notes, we listed most of these properties. We sketched the proof of some of them, but we didn't prove all of them because this is just a little bit beyond the scope of this course, and this is basically not the goal of this course. The goal of this course also to show you how to use these formulas, how to apply them. Yeah, and of course, it's better if you know how to prove them. But I decided not to include the proofs, all proofs in the lecture notes for this topic. Okay, let's just present several important properties of determinants. So we fix matrix A, square matrix, n times n, and we denote its columns by V1, V2, Vn. Again, these are columns of the matrix A, and these are they are vectors in n-dimensional space. Then the first, probably the most important property of determinant is that if you swap arbitrary two columns, the sign of determinant change. You get the same number, but multiply by -1. Yeah, this is crucial for understanding the nature of determinant. Every time you swap two columns, your sign change. So in particular, if your matrix has two identical columns, it means its determinant is 0. Why? You swap them, nothing changed, you get the same matrix, but determinant has to be multiplied by -1, but this is the same matrix. So there's only one number which is multiplied by -1 remains the same. This number is 0. Okay, so this is very handy. Of course, the same property holds for rows, but we just presented here only for columns for simplicity. The second important property of determinants, if you take any column of your matrix and you just multiply every entry of this column by lambda, by some number, then determinant scaled appropriately. Yeah, so your determinant of your new matrix is just lambda times determinant of A. Yeah, so in particular, if you have lambda to be 0, if you take one matrix and multiply each entry of some fixed column by 0, you get determinant of the new matrix must be 0. So in particular, if you have a matrix whose one column is a 0 vector, its determinant is automatically 0. Yeah, okay. This is basically what I just said. Yeah. The fourth property looks a little bit bulky, but it's actually very important. So let me explain what this means. So basically, we have our matrix A with columns V1, Vn. Then we take another matrix B with columns U1, Un. Yeah. And then suppose you have a third matrix with columns W1, Wn. Yeah, you have matrices A, B, and C, all n times n, of course. Yeah, and you assume that there exists some fixed column, fixed k. You fix some k, maybe 1, 2, or any number between 1 and n. And then all other columns different from Vk, Wk, Uk, all other columns of these three matrices are the same. So these three matrices have identical columns except one, the column with number k. But for this column number k, or the column of the matrix C is just a sum of columns of matrix A and B. Yeah. So so for columns number k, we have this equality. These are columns, kth column of matrix C. This is kth columns of matrix A, and this is kth columns of matrix B. But all other columns are identical or the same. They're equal to each other. Yeah. And then determinant of C is sum of determinant of A and B. Okay. This is, in my opinion, the fourth most fundamental properties of determinant. Why they're important? Okay, there's several reasons why they're important. One reason why they're important, if you know them, you can compute determinant of any square matrix without almost without any formulas. You can reduce this computation to diagonal matrices, basically, or even to identity matrix. If you know that identity matrix has determinant 1, and if you know these 4 properties, then you can easily compute determinant of any matrix without any formulas, just using these 4 formulas. This actually gives you another way how you can look at determinants. Determinant is some function which takes a matrix, square n times n matrix, and gives you a number. And this function satisfies these 4 properties, plus another property that this function maps identity matrix to 1. So if you know that this function of identity matrix is 1, and if all these 4 properties are satisfied, this is determinant. This is only one such function. This is very handy observation, which sometimes used in the proof of some result. Okay, but this is probably not the most fun property of determinants. This is the most fundamental one, this is for sure, but the most funny one is the next one. If you take determinant of a product of 2 n times n matrices, this is products of determinant. This is actually the most beautiful property of determinant, in my opinion. It follows from our definition of determinants, it follows from these properties, but this corollary is not obvious. Basically, this formula has to be proven. For 2 by 2 matrices, this is one of the tutorial problems which you can basically check using explicitly formula for determinant of a 2 by 2 matrix. Yeah, this is most useful formula, I might say, for applications of determinants. Okay, and finally, as I already mentioned, we had expansion formulas for rows, we have expansion formulas for the columns for determinant of a given matrix. And this basically means that the rows and columns of our matrix play similar role in computation of determinants. And this property is reflected here. Determinant of transpose of a matrix A is the same as determinant of A. Okay, so this is nice properties of determinants. We can list more if we wish, but I decided to list only this 6 because 4 of them are basically fundamental, and the last 2 are very useful. Yeah, mega useful. Okay, so these properties can be used to prove several corollaries, and proofs of these corollaries are in the lecture notes. Yeah, okay, let's list some of them. So first of all, this is very handy formula. If your matrix, which I already mentioned, if your matrix has 2 identical columns, its determinant is 0. I already mentioned this in the previous slide. Yeah, so it follows from the fact if you swap these columns, determinant must change sign, but if they're identical to each other, if they're the same columns, that of course you get the same matrix. So determinants, on the other hand, should stay the same. So it must be 0. Yeah. Similarly, this is a mega important properties corollary for determinants. If you have determinant of matrix is not zero, then determinant, and if you assume that the matrix A is invertible, then determinant of inverse matrix is 1 over determinant of A. Okay, let me repeat. So if you have an invertible matrix, then its determinant is not zero, and determinant of inverse matrix is 1 over determinant of A. This immediately follows from the product formula for determinants. Yeah, what's the inverse of A? It's some matrix such that A times inverse of A is 1, identity matrix. So you apply to this equality formula for the determinant, and you get determinant of A times determinant of inverse of A must be determinant of identity matrix, which we already computed, which is O equals to 1. Okay, and the final lemma, so if we know that rank of a matrix A is less than n, so it means its nullity is positive, yeah, but the rank nullity theorem, this implies that determinant is 0. Okay, observe that a very special case of this lemma is actually this corollary, yeah? If you know that two columns of your matrix A are the same, in particular, this means that the rank of A is less than n, yeah? Because what is the rank of A? It's a dimension of the column space. So if your column space is not the whole n-dimensional space, is not Rn, it basically means that your n vectors, your n columns must be linearly dependent, yeah? So if they're linearly dependent, this in particular means that one of these columns can be expressed as a linear combinations of other columns. We mentioned this in the previous lecture. This is one of the equivalent definitions for being linearly dependent. Yeah, but if you look here, this is exactly means that the columns are linearly dependent because two of them are the same. This is actually linear dependence relation between these two columns. So this correlates special case of this lemma. And basically to prove this lemma, you can assume that, for example, last column is a linear combination of the first n-1 columns. And then you can use properties listed on the previous slide to deduce that determinant of your matrix is 0. This is not complicated. We're not going to do this. This is done in the lecture notes. And you strongly encouraged to try to prove this yourself. Again, in one special case, this is already proven here. We already discussed the proof here. Okay, good. Now we go to a very important topic: how determinant of how to compute determinant of the inverse of the matrix A if it exists. Yeah, this part may look a little bit technical, but it's important, yeah. And you can use this part to find inverse of some matrix explicitly in many different cases. Actually, for 2x2 matrices, this is tutorial exercise. We already did this in tutorial problems. Okay, first we have to define what is adjugate matrix. Okay, so we start with matrix A, square n times n matrix A, and then we define what is called cofactor of the matrix A. You fix I and J, and the cofactor of the matrix A is the following number. What does it mean? First, you remove i's row and j's column. You get this n-1 times n-1 matrix, which we denoted previously by aij. Yeah, this is n-1, n-1 matrix obtained from A by removing i's row and j's column. Yeah. Then you compute its determinant, fine. And then you multiply it by this number, -1 to the power I plus j. Yeah, if you remember, this is exactly the number which appears in the expansion of determinant by i's row or by j's column. Okay, and we call this number Cij. It's called usually ij cofactor of the matrix A. Okay, and then let's create new matrix, which called edge-gate matrix of A, denoted like this, edge of A. And by definition, this is n times n matrix, whose ij entry is Cji. Basically, you just take a matrix whose entry is Cij, and then you transpose it. So this is a crucial point, that here I and j I swap. Yeah, I swap I and j. So basically, you take cofactors, put them into the matrix, yeah, and then you transpose it. The resulting matrix called edge-gate. Why it's important? Basically, because this edge-gate matrix almost give you the inverse of your matrix A. Note that inverse matrix for given matrix A may not exist. There are invertible matrices and there are non-invertible matrices. But edge-gate matrix always exists. We just basically here gave a formula for it. So this is why it is important. If you take matrix A, if you multiply this matrix A by its edge-gate, you get identity matrix multiply by the determinant. Okay, this is mega useful property of the edge-gate matrix. This is basically give you the recipe how to find an inverse of a given matrix. You just compute all cofactors, put them into n times n matrix, transpose, you get the edge-gate matrix, and then you use this identity, you just have to divide edge-gate matrix by determinant of A, if determinant of A is not 0. Okay, if determinant of A is 0, you get something like this, and we already know that the inverse of matrix A does not exist. And we have immediate corollary of this proposition that matrix A is invertible if and only if determinant is not 0. And since we already know that matrix A is invertible if and only if rank is n, we know this from the theorem on the first slide of this part of this lecture. So we have this nice equivalent condition. A is invertible if and only if rank is n, if and only if determinant is not 0. Okay. So basically, this is everything I wanted to say in this lecture. It's a little bit too fast for such great topic. And the topic is actually quite technical and I must say spacious. It's quite big. So I strongly encourage you to go over all properties of determinants listed here. Try to prove as many as possible. Read the proof of some properties which included in the lecture notes. Read it from the lecture notes. But the remaining proofs are contained in the book, or you can find the proofs in any decent big book on linear algebra. This is very classical and quite old topic, and I think it's very beautiful. Okay, let me stop the recording.